Good afternoon from Northwestern, everyone. I would like to welcome you to today's C2QA Colloquium. As many of you, I know today's speaker quite well, but I would like to introduce him to those of you who are less familiar with him. David Schuster is an experimentalist and expert on quantum computing with superconducting circuits and hybrid quantum systems. He received his PhD from Yale in 2007, graduating from Rob Chelkop's lab with an award-winning thesis. And in fact, this thesis is still so relevant and impactful today that I discovered that one of my graduate students apparently does not leave the house without it. After postdoctoral work split between Yale and the Chuang Lab at MIT, David joined the faculty at University of Chicago in 2011. He's one of the inventors of the well-known transmon qubit. He has been a major driving force in the field of superconducting qubits and circuit QED. His extraordinary creativity and productivity have been recognized by a number of distinguished awards, including an NSF Career, a DARPA Young Faculty Award, Sloan Fellowship, Packard Fellowship, Kavli Frontiers Fellowship by the National Academy of Sciences. I'm excited that we have David Schuster here today and to learn how to spin straw into gold or maybe build materials out of photons. Dave, the floor is all yours.
Okay. Let's see if it works here. All right, great. Well, at least hopefully the photons are making it to your screen. Let's see. So there's an echo. Okay. Let's see. Let's get our laser pointer here. Perfect. Great. Yeah. So I'm going to talk about how we can get we can use sort of all these ideas that we've developed for quantum information and start to think of them as materials and how we can build some of the capabilities that we might need to study materials using photons, microwave photons specifically. So, many of the systems that we care about in condensed matter are solid state systems, and the usual particles that are doing the work are interacting electrons in the background of an ionic lattice, and the properties of the lattice will contribute, and the nature of the interactions will contribute to the physics that you observe. It's been a trend to use ultra cold atoms, where instead of electrons, you use atoms trapped in, say, optical lattices to simulate the ionic lattice. And that's a very interesting platform. And today I'm going to tell you about how we can use photonics, specifically microwave, where the particles are interacting microwave photons, and the kind of substrate is superconducting circuits. So why might you do that? Well, it's a nice system. It's got a long lifetime. So it can even be up to a second in these accelerator cavities, like they make at Fermilab or that they use at Brookhaven. It can, but even on our more humble circuits, we can still get tens of microseconds, and we're even starting to approach the milliseconds, especially with the work that's going on in the C2QA collaborations. So they live for not as long as we would like, but importantly a long time compared to their interaction strength. So we can make the interaction megahertz or even gigahertz. In fact, there's no fundamental limit in terms of the interactions. It's sort of all interactions in a certain sense, and I think that's one of the special things about circuit QED. Just to put it in the context of cold atoms, they typically have second lifetime and maybe kilohertz dynamics. So it's a similar, at least dimensionless sense, it's a pretty similar, but faster. And the other thing, though, that's I think particularly special about circuits is that you get the flexibility of printed circuits. I think actually no one has made better use of this than Andrew Houck at Princeton and part of the C2QA in terms of making these hyperbolic lattices and these line graph lattices and things like that. And I'm sure you guys have probably heard from him about that. But another interesting thing which we'll talk about a little bit is trying to look at topology and how you can get interacting systems there. So it has nice tools for exciting things and probing things. We can measure each individual thing. We can measure things on fast timescales, but there are some challenges. One of the interesting ones that we've dealt with is just that these systems are intrinsically lossy. So if you have an electron, we sort of take for granted that the electron is a conserved particle, that it doesn't just disappear. But if we're using photons as our particles, they can just get absorbed by the walls, for example. And so how can you populate a many-body phase if you can't even keep your particles around? So that's one of the things that we'll think about. And if people are interested in this topic, here's just some references that might be interesting to you. Okay, so how's the talk going to go? So first, we'll talk about how we can just get these photons to interact. Like, what is the system? How do we set things up? Then we'll talk about this idea of how do we stabilize photons against decay. So how can we make it so that they actually stick around, so we can actually do stuff with them? Then we'll talk about adding a new capability, so building a synthetic magnetic field for the photons. And then finally, we'll talk about how, without the magnetic field, but with maybe stronger interactions, how we can actually have photons and many resonators actually interact with each other. For the first part, that we're going to try and study a model called the Bose-Hubbard model, and so it's both a simple model, but it's actually really rich. You can essentially, with the right configuration of parameters, get almost any kind of strongly interacting physics out of it. Superconductivity, the strongly interacting insulators, topological things if you get the right configuration. So it's sort of a good basic interacting model. And so the ingredients here are, first, if you want to add a photon by itself, it costs some energy. So that's like the frequency of our qubit or our oscillators, for example. Then if we want to couple from site to site, so that a photon can hop from one site to another site. That's kind of the lattice that we're in, and it's going to hop at some rate j. And for the purposes of this talk, everything is going to be nearest neighbor. So it can hop for the nearest neighbor. In principle, though, you could have long range hoppings and things like that as well. And then the interactions actually come from this term. So you can see that and what this term means is that if I put one photon, then to put another photon on the same site, it costs me a little bit of extra energy, or maybe it actually costs me less energy, but depending on whether it's attractive or repulsive. But the amount of energy changes per site, and that's going to have a really important consequences. So for example, if J is greater than U, these photons are bosons, and so you'll get a superfluid. So you'll get something where the phase is coherent across this whole system, but there's a large number of fluctuations from site to site. On the other hand, if you make U really big, then it's very hard for there to be more than one particle per site, and so you'll get just the same number of particles on every site. And so we're going to explore, actually mainly this regime in this first part of the talk. Okay, so this is sort of the abstract version. So how do we realize such a model? So we have two basic components. So the first is just an LC resonator, and that's just sort of the electrical engineer's version of a harmonic oscillator. So you can think of it as just effectively harmonic potential, and it has and you can have the ground state, you can have one photon, you can have two photons, and these transitions are say 5 gigahertz or so. And this is great, and it almost satisfies what we want. We could get the it costs energy to add particles, and if we couple them together, we can make it hop, but we don't have the interactions. And so to get the interactions, we need to use a nonlinear oscillator. And so we just replace this inductor with a Joseph's induction. And so, this is known as the transmon qubit, and we use it for quantum computing, and it's pretty ubiquitous in IBM quantum processors, Google's quantum processors. They're all based around the circuit. But here, I think I don't necessarily want you to even think about it as a qubit. I'd rather you think about it as just a site where it can store photons. But the fact that we're using this small junction as the inductor makes it nonlinear. So then instead of a parabola, you get a cosine potential. And at the bottom, it still looks pretty parabolic, and this is exaggerated. But the idea is that the next when you go from this level to this level, you get one frequency, say still 5 gigahertz. But when you go up, because the potential has softened a little bit, the energy is a little smaller. And that's exactly this type of interaction that I showed you in the cartoon picture, where adding an extra photon is a different energy. And so this transmon qubit that we've been using for years for quantum computing just naturally is one of these Bose-Hubbard sites. We don't have to really change anything. That's what it is. And so that energy scale in this case would be about 300 megahertz. It's actually negative. It turns out for the physics that we're studying in the regime that we're in, it actually doesn't really matter so much what the sign is. It's just that it has to be, the absolute value has to be big enough. So, okay. And so the next thing I want to talk about is how we're actually going to measure things. So this is the Jaynes Cummings Hamiltonian. I spent my graduate career really trying to realize the things on the slide. I remember it very fondly, of course. So it has 3 parts. It's got a harmonic oscillator, so that's the red part, and that's you can think of this as in cartoon language as this sort of optical cavity or microwave cavity. There's a qubit, which in our case is not really a qubit. It's this Bose-Hubbard site. That's in the middle there, and there's some coupling between them. And this is a form of coupling which basically just says that you can take a photon out of the resonator and put it into the qubit, or you can take a photon out of the qubit and put it into the cavity. So it's sort of this is really just the simplest form of interaction between these 2 systems. This actually works pretty much the same for 2 harmonic oscillators. Actually, it's just you just put another oscillator here, but we have a inharmonicity. So anyway, so if they're resonant, then you get this photon exchange. If it's off resonant, instead you basically go to the next order, and what you get is that this term which has the photon number and sort of the qubit occupation number in it. And so this looks like we can use this for 2 purposes. So we can use it for readout. And so this is just some raw data of a cavity. And so in this case, we first scan it with the qubit in G, and you see a peak over here. And then we put the qubit in the excited state and scan it, and you see that you get a peak in E. So there's different frequencies of the cavity depending on the state of the qubit. And so if we hook up a cavity to our qubit, we can use that to measure it. And so we measure here. If we get transmission, we know it's in the ground state. If we don't get transmission, it's not in the ground state. And there are schemes to also extend this to more photons stored in this qubit if we want. And the shift here is just given by twice this energy scale. On the other hand, and this is actually, you can think of this as a little bit like a Stern-Gerlach experiment. And this is actually the sort of back reaction. You can imagine that if the silver atoms pushed back on the magnets in the Stern-Gerlach reaction, they should feel a force. And this is sort of the force that's on the qubit from that same interaction. And so depending on how many photons, so this is like the photon number, it shifts the qubit frequency. And so we can also measure how many photons are there as well. So we won't use that in the first part of the talk, but we will use it later when we're talking about multi-mode systems. So we can use a cavity to measure the state of a qubit, and we can also use a qubit to measure the state of a cavity. Okay. And again, it's also this 2QA. And again, this is maybe for the experts in the audience, if you want to measure sort of how good this system is, you can do this with one number, which is the sort of interaction strength squared divided by the decay rate of the cavity and the decay rate of the qubit. And the goal is to get this to be larger than 1. And this is still a challenge actually in many other fields. But we're in circuit QED, we can really do quite well at this. So, we can do on a chip, you can do maybe 1 million or so, and with these 3D cavities, I'll show you later, you can get above 1 billion. So it's just to say that it's a high quality system. And if you're familiar with cooperativity and optical systems, well, then I guess you can be sufficiently jealous because it's a pretty good number. Okay, so for so we need these qubits. So this is kind of what they look like. Just a single qubit, and I'll show you a chip, sort of 2D version of this as well. We operate these things at a few gigahertz. We do that mainly actually because of cell phones, because that's where we can get test equipment easily. We have a big rack of equipment to control just a few qubits. Actually, now there's again, driven by cell phones, there's a new kind of FPGA based chip that has that I think we're hopefully going to be able to condense this entire rack onto essentially one board. And that's something we're working on as an open source effort with Fermilab, and we're actually just about having the first version out. So if people are interested in that, I'd be happy to talk with them later. And we're operating at these frequencies, which are a few gigahertz. If you convert that into temperature, the sort of thermal energy scale is about 250 millikelvin. So that's so we need to go to really low temperatures, and so we go to inside of a dilution refrigerator and operate around 10 millikelvin, and so the thermal background is hopefully negligible. And so this is a cryostat, and the sample would go inside one of these cans with lots of magnetic shielding and things like that. Okay, so now let's take a look at an actual chip that would implement this sort of Bose-Hubbard physics. So we'll start with our qubits. So we make a lattice of qubits. And so each one of these is a Bose-Hubbard site. And then they're just close to each other, so there's some capacitance between them, and that gives us the tunneling. Each qubit has a little squid loop, so that if we apply a small magnetic field, we can actually change the frequency. And so we have some control lines to do that. And this lets us tune out all of the disorder. So, unlike atoms or fundamental particles, every qubit is a bit of a snowflake. They're all a little different. We try to be able to make them consistently, but they're not all identical. But using these flux bias lines, we can kind of do some fine tuning to sort of trim them to be the same. And the other thing we can do is if we want to measure things separately, we can pull them out of the lattice. So we can dynamically tune them either all to the same energy or to separate energies. We want to be able to measure the state. So, we kind of like the equivalent of like an STM for our material. So the way we do that is we actually just give each qubit its own readout, and then we can read out each of these qubits individually. And then in order to stabilize them, we're going to need these two extra elements. So we need another line for driving just this last qubit. And then we also need a special cavity that's not used for readout. You can see it's more strongly coupled, and this one is actually used to sort of remove entropy from the system in a way I'll describe in a little bit. Okay, so these are our components, and okay, so now what we're going to do is just do some basic measurements to try to ascertain the properties of this system. So in order to, first we want to measure the qubit frequency. And so if we do spectroscopy on the qubit at a low power, we will see a little dip here, and that indicates each site's sort of 0 to 1 frequency. And so that's a little less than 5 gigahertz. And then we'd like to find out how much that interaction term. So how much does it cost? What's the difference in frequency to add second photon? So what we do is we first excite the qubit. We put exactly 1 photon in it by applying a pi pulse to the qubit, and then we do spectroscopy again, and then we see that the peak moves to here, and so we now know that this U is about 250 megahertz or so. Then what we can do is, if we take 2 of the qubits out of the lattice, the two that are next to each other, and we put a photon in one of them, and then we tune them into resonance, and we look at how that photon oscillates back and forth. So this is like in Q6, and we put it in, and we just, if you, depending on how long you wait, it oscillates back and forth. This frequency of oscillation is this J, so we can measure that. Another way of kind of getting at similar things, but I think it also is kind of nice because it shows you, it already starts to look like a bit of a material, is you can, if you just, if you bring them all together instead of just two of them, and then you do spectroscopy, instead of seeing something like this, what you actually see is that essentially this line gets split into a bunch of different lines. One for each qubit. And these are actually the kind of the normal modes of the system, or if you're thinking more like a condensed matter physicist, this is like the density of states. There's not very many states, so we can actually resolve each one. But you could think of this as like the equivalent, materials equivalent of like doing ARPIS or something like that, where you measure the band structure of the material. And you can, and this was done on Q8, and you can see like which modes have more participation in Q8, things like that. The last thing is just you need to measure how good the qubits are, how long do they last, both in terms of their relaxation time and dephasing. And so we measure this as a sort of as a function of detuning from their readout resonator. And I think the important thing, so this is where the lattice is, and the important thing is just that it's it's pretty good. It's a low sort of kilohertz range. So we can take all of this data now and we measure it for every qubit and all the nearest neighbor pairs of qubits, and we can make this sort of summarize it all into this chart. And I think this is really kind of the key idea and sort of to a lot of these sorts of experiments, is that you need to get this hierarchy of energy scale. So in our case, we're trying to get into this Mott insulator regime, so we want the U to be much bigger than J. So that's here. So these are the sort of the two coherent energy scales. Then there's disorder, which just would maybe obscure some of the physics, and then there's dephasing and relaxation. And so this is how long our particles will live. This is kind of sort of telling you about disorder in the material. And so just like if you're trying to make a crystal and do condensed matter physics with a crystal, you need everything to have low disorder and long lifetimes and things like that. Then it's a similar thing here. And so I think the fact that we can get this hierarchy is really good, and it's a strength of the platform. Okay. So so this is great. So now we can go and we can measure our Bose-Hubbard model. We have it here. It's very nice. It's in the right regime for the Mott insulator. And so if we measure it though, what we're going to measure is actually not very interesting. It's just the ground state. So we'd have some sites here, and they're just there'll just be no photons. We'll just measure vacuum, and that's so it's not going to be very interesting. And the reason is that there is some finite lifetime to things, and so if you wait for a long time, it's just going to go to vacuum. That's still the sort of the ground state of the system. And so what we need is a way in which we can stabilize the state to actually have photons in it. We'd like a sort of the equivalent of a chemical potential. And what we're going to do here is not quite a chemical potential, but it serves a similar role. And in fact, in many ways, it's more powerful because you can tailor it in sort of different ways. You're not just doesn't just have to be sort of a chemical equilibrium. And so here's the basic idea. So the idea is that what we need is a source of photons that can replace any photons that are lost here, but we want certain properties. So let's kind of just explore this a little bit. Let's say that we have a magic site here, which I'll tell you how we realize in a bit, that just produces one that always wants to be in one photon. It doesn't want to have two photons, doesn't want to be in the ground state. It just always wants to have one photon. What would happen if we couple that into this lattice? Well, since now there's a tunneling between the site to this site, so it can hop over to there, and that's great. And now this guy's over here, so it can actually tunnel over to here. And also this guy, again, is our magic lattice site. It wants to always have one photon, so the photon will be replaced. So it's gonna hop over. But now this spot is free again, so this guy can hop in. And also, yeah, that one can move. This one can hop in, and that can continue until the whole thing is full. And now you ask, well, what happens now? And what happens is that the thing has to stop because of this anharmonicity, because of the U, this guy has the wrong energy. It actually has too much energy, but there's no state here. So if it tried to hop here, there'd be no way to get rid of this extra energy. And so it's blockaded. Similarly, if one of these guys wanted to double up, it can't do it because for the same reason. For this very simple many-body system, these two, this kind of many-body gap and this particle addition gap happen to be the same. For other kinds of many-body states, they could be different. But basically, these two things have to be true, and then the thing will kind of stabilize. And similarly, you might say, well, how come this guy doesn't go back? And it's basically for the same reason. And so we can stabilize this mod insulator such that if we can make this site, then if we just leave it for a long time, we can come back and measure it, and it should just stabilize into this insulating state. And so how do we make that site, though? That's the question. And the way we're going to make that site is we're going to use another qubit, so that this last qubit is a little bit different than the other ones. And what we've done is, and so what we're going to try and do is we're going to try to put 2 photons in and then have 1 photon decay back down and the other photon decay into this reservoir. So we're going to add another reservoir with another coupling, and we will, and this one we want to be much faster. So we want it to decay so that this photon should decay much faster than this photon. And so we apply a drive at half of this frequency, and so it misses this guy, but it hits this guy. So you can have a pair of photons that hop in, and then one of them is going to come over here and then instantly decay, basically, and the other one's going to fall down or coherently get moved over here when this one goes over there, and then and now. That one instantly decays. This one is going to now take a very long time to decay. So it's sort of stuck there for a while. And so if we turn on this drive and tune everything up right, you can watch the dynamics of that site. And what you see is that there's this one goes up, the n equals 0 state, which was very high, goes down, and actually you get a little bit of 2 population, and that's basically well partially because you're actually spending a little bit of time there, and also possibly you may have if you actually have some hot, this resonator wasn't in this experiment wasn't perfectly cold, and so if there's a photon here and you're like this, then you can actually go back to this state. That's where that comes from. Okay, so we now have our magic site, and so now we can actually look at what happens to the real system when we turn this on. So we turn on this process, and so what's being plotted here, these are the sort of the site numbers or the qubit numbers, and this is time. And so we turn it on, and what you see is this kind of evolution. And what you can see is that just like in that kind of cartoon I showed you, there's kind of a bit of a wave front of the particles coming in, filling things up, and then and so after roughly 2 bounces, it's mostly full. Maybe that you can sort of see a third sort of wave here, but then it gets pretty full, and we get about 90% occupation of each site. And you can, if we want to look at this more quantitatively, you can take the slices of this and plot them together. And what you see is that the last site is involved in the stabilization, so that one's like 50%. But then the rest of them are all going up and are pretty high. And again, I think we believe that the reason it's not
popping in right there.
I think the reason that it's not perfect is largely due to these thermal holes that sort of do the opposite of what you want. We think that the lifetime is actually pretty long, so we don't think that's what's limiting it. Okay, so so now so one thing we wanted to investigate a little bit was what like the dynamics of how, okay, so you've stabilized it, we saw it stabilized, but what could happen is one of these sites could decay. Let's say this site could decay. And so what are the dynamics of the refilling process? And so what we did to simulate that is we kind of made them on insulator, but we took one of them and we kind of had it detuned. We had it up here, and then we sort of suddenly bring it in here, and that's like putting a hole into the system. And first we did it with the stabilizer off. So we turned the stabilizer on, we made the state, we turned it off, and then we put the hole in. And so so when you do that, you can actually see what's a quantum random walk, and it's sort of mostly ballistic. Well, it's actually kind of ballistic in the whole case, and you might actually think that this is due to dephasing or disorder in our system. It's actually not. If even the theory curve for an ideal system looks pretty much like this, it's actually the fact that this isn't a light-like system that should just propagate. It's actually it's a band structure with like a cosine dispersion, and so that dispersion is actually what's doing this. It's almost deceptive how how it starts out looking pretty straight, but actually there's dispersion here. And now the question is, what happens when we turn on our stabilizer? When we do that, then it basically hits this wall, and then it basically disappears. You can see that a little bit of it is reflected, and then it gets absorbed here, and it's almost all gone. So basically, and incidentally, this was one of the things that we were trying to design. Designing that coupling between the sort of stabilizing qubit to the rest of the lattice sort of determines how well this happens. If you make it too small, then there will be some kinds of normal modes of the system that you won't be able to stabilize, and then you could end up having defects that you can't get rid of. If you have it too large, it'll get everything, but it'll be sort of poorly impedance matched, and you'll get more bounces before it gets everything. And this has been really interesting for us because you don't really think about the process of thermalization, like how you actually, if you have a chemical potential in the system, you don't really think about it. Here, because you're sort of building it one atom at a time, it really forces you to think about exactly, what matters when you do this. It also makes you realize that, condensed matter systems are tremendously inefficient at thermalizing. It's just that everything happens so fast that we don't notice that. Okay, so now so we've shown how we can make a mod insulator, and we've shown how we can stabilize these photons. I'm gonna now kind of switch gears a little bit and talk about how we can now add a synthetic magnetic field for that. So there's a lot of ways you can do this sort of thing. You can we did some. It turns out these synthetic magnetic fields, or these topological band structures, they're kind of a property of linear band structure, and so you actually don't need anything quantum to do it. You can just do it with oscillators. And John Simon and I, who have been collaborating on all this work, for us, that was actually exciting. It meant we could just play with it and do stuff. So we actually built, or our students built some circuits out of just L's and C's on PC boards. So we built a 2D time reversal topological insulator, and then sort of the 3D version, which is this Weil semi-metal. This one was particularly fun. But those actually, it turns out, because they are time reversal invariant, both of them, it's actually quite hard to add interactions into the system while they're sort of only protected by this symmetry. So if you don't maintain the symmetry, which is hard to do, it's hard to really get the interactions there. So we've decided to do a time reversal braking system, and in a more microwave sense that we can then cool down. And so so this paper was us doing it at room temperature, and we kind of were able to see all the band structure and all the topological properties. And now what we'd like to do is actually make this and couple it to a qubit. So when you're trying to make a synthetic magnetic field for photons, like what are you really trying to do? Photons, right? They don't have a charge. So if you put a magnetic field, nothing will happen. The way I like to think of it is through the Aharonov-Bohm effect. So if you have a charged particle in a magnetic field, and and you send it around in a loop, it'll pick up some phase. which is known as the Aharonov-Bohm effect, and that's proportional to the magnetic flux. But mathematically, we can sort of take this, that sort of really is what happens mathematically if you write down like the Hamiltonian or the Lagrangian. That's how it comes in, is through this Aharonov-Bohm phase. And so you can kind of do it the other way. If you can realize an effective phase when you go around a loop, it will behave like it's in a magnetic field. And so all of the properties that you're familiar with from, the integer or even fractional quantum Hall effect will happen as long as you can make it such that if you have a flux you go around, you'll get cyclotron orbits in the bulk, you'll get these sort of, magnetoplasmon skipping orbits on the edges that are topologically protected. And so the question is, in some sense, how do you get this non-reciprocal phase that you get from the Aharonov-Bohm effect without for photons that don't have a charge? And the trick of it is basically you make a normal lattice like you would, but if you can replace one of these sites with a site that has a non-reciprocal phase associated with it, you can do that. So basically a site where going this way gets you one phase, but going this way gets you a different phase. So that's the trick. And let me show you how we actually do this. So first our sites. So our sites are going to be cavities, and they're just these nice coaxial evanescent cavities that were developed at Yale. So that's kind of a 3D image of what it looks like. And then a thing that we realized is that, and this actually also, it was sort of a key realization for our multimode stuff, was that so we wanted to couple two of these sites without while still keeping everything evanescent. And it turns out if you drill from the back, you can actually do that, and then you can make and so there's a little bit of overlap between these sites, and you get tunneling that way. So that's sort of the things that we showed so far, except no. And then we want to break time reversal symmetry. And so what we're going to do is, I'll show you a detailed slide on this on the next slide, but is we're going to make a cavity, a special cavity that has 3 posts instead of a single post. And we're going to put what's called a yttrium iron garnet sphere. So it's a ferrimagnetic sphere. And you can, you'll be able to think of this as a big spin and with a little magnet underneath to bias it. And then lastly, we're going to add our qubit. So we're going to have a qubit that sticks in and couples to one of the sites of the lattice. And for now, we'll just put one qubit in there, and we'll be able to see some chiral cavity QED stuff. If we were to put in, we were to replace all of these sites with qubits like we did in the first experiment I showed you, in principle, we could get a fractional quantum Hall system in this, but for light. So this is what it physically looks like. This is it's a big chunk of niobium, and we're doing a relatively small lattice here, just 5 by 5. It's sort of the smallest that has a definite bulk and a definite edge. So that's why we choose that. And then and so you can see most of the sites are the simple type of site. If you can squint there, you can see the coupling. There's also the special chiral site. The magnets aren't, the Yig spheres aren't in here, but the next slide you'll be able to see them. And then there's a spot for 3 qubits. Currently, we just have one of them in there, but and that's how we'll couple to the edge. So this chiral site is sort of the magic piece, and so maybe I'll explain that a little bit. So there's 3 posts. So one post gives you a mode. If you have 3 posts, they all can act together to give you a fundamental mode. That's this green mode here. But then there's almost like a P state like thing where you basically have a mode that's X and a mode that's Y, and they're degenerate. And so if you but since they're degenerate, you can pick any combination of them, including X plus IY. So that's the mode I've plotted here, and this animation is of the magnetic field. And so if you kind of stare right at the center and try to ignore the outside, what you'll see is that the arrows in the center are moving around in a circle. They're just processing around in a circle. And so if you bias, and if you think of this Yig sphere as being a big spin, and we put a magnet underneath in the vertical direction, then the spin wants to precess in the same sense as the field. And so this is one mode. There's 2 degenerate modes. There's one that goes counterclockwise and one that goes clockwise. And one of them is going to precess with the spin, and the other one's going to precess against it. So the one that precesses with it is going to interact very strongly, and the other one is going to basically not interact at all. So you get a bright mode and a dark mode. So you've got the YIG mode coming up like this. And basically it's at the same like 2.8 gigahertz or 28 gigahertz per Tesla that the electron spin gives you. And then you see that there's this red mode, which has a very strong interaction with the mode. And then there's this blue mode, which has no interaction at all. And you might think that if you're going to try to take a magnet which breaks time reversal symmetry and try to make a mode that breaks time reversal symmetry, you should use the bright mode because that's the one that has part of the magnet. But actually, if you look at it, this one is chiral, but the dark mode is also chiral. It's processing with the opposite sense. They're both of them are valid modes, and we like the dark mode better because you can see that it's almost insensitive to the magnetic field. It only has a very weak slope, so it's not affected, and that's also true for any losses that are in the magnet. In the magnet, it's first order insensitive to them. It would ideally be even less slope, but you can see that there's because there's if everything were perfectly uniform and nice, this would have no interaction. But because there's some gradients in the field and things like that, you get interaction with higher order modes in the YIG. So the one that you'd like to interact with is just uniform precession, but there's sort of higher spin wave modes. And what we're going to actually do, because we want to be in the superconducting regime, is we're going to actually be down sort of over here. And you see that even well below where you get the biggest splitting, you still have like a good 100 or 200 megahertz of splitting here. And it's very flat for the dark mode, and you're not near any of this stuff. So that's where we're going to work. If you take this and you calculate the band structure, so if you take like a strip of this and then kind of calculate like a block band, then you get this is the band structure that you find. There's there's four sites in the unit cell here, and so you get four kind of bands, and then there's these topological edge modes that are on the top and on the bottom. And we can do spectroscopy on this. The way we do our, what's nice about this cell is about an inch. So instead of an STM, we just put an SMA connector on every site, and we have a little switching matrix, and we can probe any site we like. And so we can measure, if we measure two sites in the bulk, we can see that modes that are kind of in the bulk bands tend to light up, and the ones in the edge don't tend to light up very much. And if we go on between two edge sites, we see that things on the edge tend to light up and things in the bulk don't tend to light up. There's still some, you can still see them a little bit because again, this is a pretty small material, so there's some interaction between the bulk and the edge. And then we can actually also observe these cyclotron orbits and these skipping modes. If we now look at it as a function of space, so this is sort of, if we look at this frequency, let's say, and then we look at the sort of the participation of each mode. So we basically look at what is the Q of sort of driving in each mode. We see that there's more, basically it's all in the edge for this guy. And then if we drive in the bulk over here, we see that it's basically all in the bulk. This is data. So, and we can also we don't have to do this statically, so we can do this with like a network analyzer, but we can also just hook it up to an oscilloscope, and then we can actually plot this versus time. We can actually see that like this mode is actually like chiral and going around in one direction. And you can also see it's at least somewhat tolerant of disorder. So that's really nice. We can be a bit more quantitative about it if instead we just plot these sites and then take individual time traces. So this is a similar kind of data. So this is the site number on the edge. So we're just going around the edge here, and then we measure versus time. And you can see that for the sort of red mode, it's going one way, and then for the blue, it's going the other way. So we can see that these modes are in fact chiral, and there's big energy difference between them. We can also the other thing that again, if you're not like super familiar with this field, there's a lot of people doing metamaterials in this thing. It's pretty easy to do because again, you actually can do it with purely linear physics. So people have done it with like we did it with the LC circuits. People have done it with sound. People have done it with, photonic resonators. People have even literally done it with pendulums. There's a group in ETH that just made like 100 pendulums and a couple of them. And you can see at least some of this type of physics. But actually, most of those actually, if you sort of said, well, what about if you put a single quanta of energy in it? How many times would it go around? Usually, actually, the decay time is like one site, and it's just so you just put a ton of quanta in there, and then you can, even though it's exponentially decaying, you can still track it for a while. But here you can see that it's the decay time is this sort of 3 microseconds or so, and you can see that each one of these little wiggles is essentially how is one round trip, and so it's going around many round trips before it goes. So it really is exploring the whole system. So that's really, I think, a requirement if you want to see eventually see some strongly interacting topological physics. So that's really nice, and it's sort of afforded to us by using the superconducting cavities. Okay, so now we want to add the qubit to the mix. So again, this is the qubits on one of the edge sites, and so this is sort of, I don't know, my version of the of kind of a little cartoon of the energy diagram. So the qubit has G, E, and F we're going to use in this case. And if you sort of go over here, this would be like adding one photon to the lattice. But the lattice has it's not just a single mode anymore. It actually has this sort of band structure, or well, there's still just discrete modes, but there's just like 25 discrete modes here. And we'd like to be able to explore this and do spectroscopy on it, but using the qubit as a kind of a single photon detector and manipulator of this thing. So we'd like to be able to put in single photons. We'd like to be able to take out single photons. We'd like to be able to measure single photons. So the way we're going to do this is we're going to use essentially a trick that was developed also at Yale. So we're going to put it in the, so the excited state of the qubit will actually hybridize with these modes a little bit and shift. And so if we go to the F state of the qubit and drive to E, then we can enable swapping between these states. And YF instead of from G, there's just some technical reasons why that makes sense. But that's sort of the idea. And if so, if we kind of drive here, the sort of the vacuum fluctuations and stuff can drive a swap here. And so you get this oscillation, which is we like to call it a stimulated vacuum Rabi oscillation, but this is a single photon moving back and forth from one lattice site to the qubit and so forth. But there's many modes, so we can sort of scan over the band structure, and basically this is very similar to the spectroscopy from one of the edge sites that I showed you before with the network analyzer, but now instead of a network analyzer, we have a qubit. And because the system is actually very coherent, we're not just sort of incoherently adding photons to the system, but we can put a photon in, and then if we try a little longer, it comes back and so forth. And in fact, in some of these edge states, if like here where they're overlapping, if you do it here, you're actually sort of simultaneously occupying multiple edge states, which is essentially launching a pulse that's actually going around with a current sense of it. And so we can actually really see that we have a strong coupling cavity QED interaction with this chiral system. And the other thing we can do is we can use the qubit as a photon detector. So if we do say put something in with a network analyzer, we can actually measure exactly how many photons are in each mode, and so we can actually analyze that. So so we're quite excited about that. And then, okay, so now we'll switch gears one last time. And so it's interesting because it's chiral. It's also interesting just because there's many modes here. And so now I want to focus more on just pure multimode. So we're going to take away the synthetic magnetic field and just talk about we're going to take multi-mode and strongly interacting physics and do that in the form of a multi-mode photon blockade. And it's a pretty cool interaction, which I've never actually seen anywhere else. First, just a bit of a technical thing, which I think is fun and really enabled a lot of this. the way we do this, so we want our cavity is just basically going to be a box, but we'd like this box ideally to just be made out of one inside of a solid piece of metal, of ultra pure 6/9 aluminum or niobium or something like that. But the issue is that the normal way you make a box is you cut it in half and do it, and as was shown at Yale, there you can have leakage out the sides, but of course, if you have one hole and if the diameter is much less than the wavelength and it's long enough, that's fine. And so actually, if you have more, it's exponentially fine, in fact. So as long as you make the holes deep enough, you can have as many as you want. And if we use the same trick that we sort of learned when we were learning how to couple our synthetic magnetic field lattices, if we make them overlap, we can get a region which basically forms this. And even though this thing looks like, we like to call it a quantum flute, because of all the holes, that you can literally see through it. But from the perspective of the microwave photons, there's nothing they can't get out. You can also do this in cylindrical geometries, and you can make lots of different shapes. This is one example, and this is another example of it. And we've been able to see quality factors that are 80 million for the rectangular ones, and maybe 25 for the cylindrical ones, and these are about as good as we get using this is as good as we can get. I think for our very best niobium cavities, we've been able to get now up to 600 million. These are for aluminum, but we haven't really started using those for qubits yet. So this is a nice way of doing it, and then you can extend this to make a much longer cavity. So we just take this cavity, so this would be like one mode, and we just make it really long, and so now there's many longitudinal modes. But it's sort of the same idea. So we have a transbond, it's coupled to this long cavity, and it's also coupled to another short cavity for readout. And that's kind of what it looks like physically. And we can now measure the longitudinal modes of this cavity. And you can see that they have, we kind of tailor the dispersion to make them more or less uniformly spaced. And so they start at 5.5 and they go, they keep going, but we use sort of this 2 gigahertz range. And what you can see is that, yes, we have about 9 modes that we use. The Qs range from 70 to almost 100 million. The lifetimes of these things are 2 milliseconds, and the coherence times are like 2 to 4 milliseconds. And they also, and we can measure how strongly they couple to the qubit, and then it's a few megahertz basically. And so, much better than the stuff we saw before. And so this is a good playground for exploring, interactions, because we just, we can see smaller interactions and they can be significant. So I already showed you there's different ways you can interact with a multi-mode resonator. So I already kind of showed you the resonant charge sideband interactions with that we just did for the chiral one. Another way you can do it is you can use snap gates, which also was developed in Rob's group. And you can do that with either analytically or with optimal control. Another interesting one, which was originally developed in Benjamin Howard's group, is the idea of a photon blockade, where if you can prevent certain photon numbers, then you can also manipulate the state. And I'll show you how we can do that both with a single photon, and I think just they did a very nice job. Ours is better now because it's a couple of years later, but so I'll show you that for understanding. But then we also have done a multi-mode version of this, where you can actually have multiple photons in multiple cavities, and you can make a blockade. And this is a really weird interaction because it's both many sites and many photons potentially. So, and it's a very pure interaction. So there's no interaction until you sort of hit a wall. So it's sort of a pure multi-mode and multi-photon interaction. So in order to understand this part, you'll need one more thing. You kind of, I'm going to show you a bunch of pictures of Wigner tomography, and if you're not in the Yale group, then you may not know what this looks like. So just wanted to give at least a key, not necessarily explain the full thing, but just give you some key facts. So a coherent state just looks like a blob here. And if you, that's vacuum, and if you want a coherent state, that's just displacing this. A single photon Fock state looks like this, and it has a negative center region. It's like rings, and the negativity is sort of means whenever you see the blue, it means something is non-classical. And if you have higher Fock states, you can count like the number of red rings, and then that tells you how many photons you have. And there's also these sort of cat-like things, which basically look like two displaced things with some fringes in the middle. And just so you kind of get a sense of the types of things that you might see here. And the way we do this is you basically, to get these pictures, we basically displace the cavity and then measure parity. That's sort of what's being plotted here. Okay, so if we just have a regular cavity, we can only generate sort of classical displaced states, because if we drive from 0 to 1, we're always going to get some to 2, and so it just looks like this. So we have this blob, and if we put a coherent state on it, it just moves. Okay, and that's fine. But now, if we can put a blockade on it, if we can block it here, what you see is that it sort of hits this wall and then interferes with itself to give this blue. And you can see that it actually is making this, going from 0 to 1 to 0 and superposition. So it's actually, we've made like a qubit here. So the way that we do it is, the way this blockade works is that we are driving. So remember that the photons are, I showed you that the photons peaks are number shifted. So, so if I drive, the qubit frequency from G to E is different from if there's 2 photons versus 1 photon versus 0 photons. So if I just drive the qubit at this frequency, that's going to cause the level to sort of split. And what that, if I drive it on resonance, it'll split. If I drive it off resonance, it'll kind of get pushed around a little bit. And the point is, though, now if I try to go from here to here, there's no level in the middle anymore. It's been split, and so I will miss, and now I can't do it. So that's sort of where the blockade comes from. I can basically push around the level so it's at the wrong frequency, and I can do this at 2, and I get a Rabi oscillation. And this was, I think, really first done by Benjamin several years ago. If you can also do this for higher Fock state numbers, so you can go to 3, and now the sort of radius of the circle gets bigger. And you can see that this looks sort of like the 2-photon Fock state that I showed you before, but not exactly. And that's because this is not, now there's 3 states, and so this is ensuring that I never get 3, but it's not really telling me, how much 2 versus how much 1 I get. And so, but we can use the optimal control, and we have kind of our own framework for this. Yale has always also developed a very nice one. But if you put in the sort of the effective Hamiltonian that you get here, use optimal control, you can sort of displace, and instead of doing a uniform displacement, you can sort of do this kind of funny shape, and then what you see is that now you can make it perfect, and you can make whatever state you like here, and you can see that. So we blockaded here, and then you can see that we can actually get all of it into 2. So that's interesting, but sort of an extension of previous stuff. What I think is really neat is that we can do it with all these multi-modes. So the modes, I showed you that modes, have some different chi's, but some of them have, so this would be just like mode 6 and mode 2. But actually, like the nearest neighbor modes actually are pretty similar, and we can also use some techniques to dress the kind of modify these chi's dynamically with extra drives to sort of make them more similar or more different if we want. But we'll just select for a moment these 2 modes, and you see these have almost the same chi. So if we were to, put a photon in the system, we wouldn't actually, if we drive at this frequency, we'll blockade it, but we can't actually tell whether it's 2 photons in 1 qubit. So basically, this is the qubit spectrum, and we can't tell whether there's 2 photons in mode 5, 2 photons in mode 6, or 1 photon in mode 5 and 1 photon in mode 6, right? All of these will give the same shift to the qubit. And so so that means that if we blockade it, it's actually, since we can't distinguish it, it's actually it can entangle the 2 modes. So if we we drive mode 6 with this on, then what you see is that you get an oscillation. And if you drive, so it looks like a qubit. If you drive mode 5 with this on, it also looks like a qubit. But if we add a photon to mode 5 by say we stop here, so and then we drive mode 6, then you see nothing happens. And that's because there's already a photon there, and so trying to drive it again would move it up to there. So so this is like kind of like a C naught or something like that in some sense. And so that's an entangling gate, and it's a very interesting interaction, because basically at especially if you imagine going up to higher photon numbers, they're not interacting at all until they get to n-1, and then all of a sudden they're very strongly interacting. And so we can use this actually to make entangled states. So if we want to make a Bell state, for example, we can do this with 2 modes. And so so we do exactly what I just said, but now we just drive both of them at the same time. And then if you wait for the right amount of time till here, you actually get a Bell state. And that's sort of right, now, I guess. And you can see that both in the density matrix and also in the Wigner tomography, that you get these sort of correlated states. And you can also see that there's a lot of data here, and it gets hard to do this as you get to more and more. So, okay, so then you can also do this with 3 modes. So the way I like to think about this is that you basically make a hyperplane, right, which has a constant number of photons. So in this case, it's 2 photons in 3 modes. It could be 3 photons in 3 modes, or it could be 2 photons in 5 modes, whatever. But there's some plane, and basically the dynamics inside here are totally free. They're not interacting at all. But if you hit the wall, then you have like a hard wall kind of interaction. I think sometimes I like to think of it as like quantum jamming or something like this. But anyway, yeah, so now you can do this with 3 modes, and you can make, in fact, if you do this particular one where you blockade 2 with any number of modes, if you just displace all of the modes together, you'll get a W state. So you can make, again, you can measure it. And I mean, I find, unfortunately, like these are less and less meaningful. And you can look at the density matrix and you can start to extract witnesses. But yeah, we can also do it for 3. And we've also done 4 and 5 modes and other things as well. But anyway, it's just kind of nice that we can do these kind of interesting interactions. So there's other stuff going on in the lab. I'll kind of finish up now, but we try to make new types of qubits. We try and do autonomous error correction. We've been using qubits to help with some dark matter searching, trying to do circuit QED with electrons on helium. Things with millimeter waves at 100 gigahertz. Can we do circuit QED at 100 gigahertz? And even some atom superconducting hybrid stuff. So, if anybody's ever interested in talking about that, feel free to get in touch. So, of course, I didn't do this work. This work was done by the people in this picture. In particular, almost all of this work was done jointly with John Simon's group. Alex Ma is the postdoc who did the first 2 experiments on the mod insulator and the chiral cavity QED, along with Clay, and then and Brendan and Gabrielle and Meg is starting out on that project, and then we've got Watson who's led the multi-mode stuff along with Kevin and Andrew, and we've gotten to work closely with Liang and Manhao. So I'll just leave up the conclusions and take any questions.
Thank you very much, Dave, for this very clear and inspiring talk. I don't see questions in the chat yet, so please, if you have any, put them in there or raise your electronic hand or just speak up. Meanwhile, Dave, you can imagine in this moment of Zoom silence, just imagine a round of loud and enthusiastic applause. And while we wait for questions. I see clapping hands, no raised hands yet. I had a simple, quick question. So you mentioned these interesting cavities, some rectangular, some cylindrical, and I think it showed that the cylindrical had lower Qs. What's the reason for that?
I'm not totally sure. Probably some. I mean, we made less of them, so I mean, because it was a little bit more of a pain to actually make it, and so that's. I mean, probably that's the main reason. Honestly, I think that the sort of like the surface area to volume where like where kind of the edges are, which may be a little less clean than sort of where it was smooth, might be a little worse for that one. But yeah. Not really sure. I think mainly just we didn't do it as much.
I see. Thank you. Now there is a question. Guan Yu has his hand up.
Hi, Dave. Very nice talk. So bit curious about multimode. If I store my quantum information in this multimode cavities, so I assume each mode will kind of have a photonic qubit. And then could I use this to simulate some synthetic dimension? So for example, if I have an array of this multimode cavity, so I somehow get an extra dimension, I can use that to simulate either physics or maybe to do some quantum error correction with in a higher dimensional code.
Yeah, so yeah, that's very much along the lines of what we're thinking. So I would say, I think one thing I learned in Rob's group is that it's fun to, it's kind of fun to develop the quantum information stuff alongside sort of the, let's say, condensed matter with photons in that. And so, I would say the main reason we've been developing these multimode cavities is because it could be good as a quantum memory. So you can use one qubit, say, and multiplex it to many cavities, just because the cavities are so much longer lived anyway, and that can be really good in terms of reducing the control overhead and things like that. And also just there are new types of codes that are available with multiple cavities that you can't do in a single cavity. So I would say that's probably the main thing that's motivated it. But then, as you say, it's an interesting venue for exploring these sort of exotic interactions, or for making you can make also multi-cavity bosonic random walks. Which is sort of one way of getting more dimensions. You can certainly you can have multiple multimode arrays to get higher another dimension that way as well. So yeah, I think all of that's really interesting.
So you think it won't be too crazy to think about some 4-dimensional system in the end? Maybe in a few years.
I don't know. I mean, it sounds pretty crazy, but I like crazy.
Okay.
Excellent. There are more questions, one or two that I received as direct messages, so I will read them out. So how about IR-based quantum states to move away from cryogenics to room temperature operation?
Well, of course, there are a bunch of startups trying to do this, like PsiQuantum and Xanadu and stuff like that, and they will claim that that's the only way that it could possibly work. The problem that they have is that there aren't really very many good nonlinearities at those energies, right? So in materials, the nonlinearities tend to be pretty weak, and so they end up trying to use measurement-based quantum computing and things to get around it. So it ends up being a pretty different paradigm and of course you can use atoms, and that's interesting, it's sort of another different degree of freedom.
There's a second question which went to me privately, which is, could you discuss the effect of the damping coefficient, so Q of the cavity or circuit, on the dynamics of the system as well as time constants?
Sure. So, well, there's a couple of things. So, when we were looking at so in the mod insulator, actually, surprisingly, it wasn't so bad, because if you sort of you could see that it would fill up in like basically 2 or 3 round trips, and the decay time was sort of probably 100 times that or something like that. So and so what, there, I think, you lose a photon every once in a while and it gets replaced pretty instantly. So it doesn't I don't think it really affected that experiment too much. In the chiral cavity QED, because there's all the magnets and stuff, all the Qs were lower. And so there you could see that, we didn't have infinite time, like our oscillations didn't look perfect like they did with the multi-mode system. And even the multi-mode system, right? I mean, it's really, really long lived, but we're doing kind of more exotic things that are at higher order. And so a lot of the things are slower. And so you do start to notice it there. So, I mean, it can of course hurt the coherence, or it can just make things go away before you have time to do the interesting things.
Thank you. And then there's another question which I think is sort of, how quantum is some of this? So Carlos says he understands that the demonstration of chiral modes via acoustics or pendulums is ultimately rooted in classical wave mechanics. And is that different in your experiments?
I would say, I mean, yes and no. So I would say it's different in the sense that, like, we really are working with a single photon, and we can, manipulate single photons, put them in, put them out, put them into superpositions of states, entangle, we can entangle them between, different modes and things like that. So in that sense, it's very, it's very, very quantum, right? It's, but in another sense, I think, at least what we actually did was, we only put one photon. So on the one hand, putting one photon in is very quantum because a photon is quantized and it's very quantum. But on the other hand, since it's only one, it's not so different from the linear physics, right? If we put two in and they were interacting, then you would really see it more. And so I think that that's something that we'd like to do, is we want to put another qubit in there and be able to, show that we can have qubits interacting via this medium. And we want to show that, we can show, photon collisions and things like that. So I would say that the system is pretty quantum intrinsically. I would say that the experiments we've done, we haven't really exploited that to its full potential yet. But those are upcoming.
Thank you. I had one more question. You made a side remark that thermalization in condensed matter systems is inefficient but fast, and I saw Steve Gurn was knowingly nodding his head, and I didn't understand it quite. Could you clarify how inefficient and fast go together?
Yeah, sure. So, in our system, right, like you could see like exactly how many times it had to interact with our kind of reservoir in order for it to be thermalized, right? So if we put in a hole, it's like 80% gone on the first interaction, and and each bounce. Now, but let's say we wanted to make something that was like really broadband, right? So then we would have made that coupling much larger. And then what would have happened is if we made it 10 times larger, it actually would have to bounce, it would be sort of mismatched. So it could cover a much wider, energy range of particles, but it would end up bouncing 10 times before it did that. And so the in a regular condensed matter system, right, you can sort of think of this chemical potential as being at like the Fermi energy or something like this. And so when there's holes moving around at some lower energy, right, they're interacting. Usually there's a big bulk, and you're only thermalizing at the edge. Often like there's like one wire at the edge, so there's a surface to area to volume argument, but then there's also a just like this energy kind of phase-based density of stuff argument and so things are mostly not exchanging energy, but because the interaction scale is femtoseconds or attoseconds or something like that, even on the time scale of most electron dynamics, it's pretty fast for most materials. And that makes it really robust, right? So I mean, I'm not saying that they're that real materials are bad. They're super robust because they've kind of in some sense they're like over damped or something like this, or they're we had to sort of use each particle as much as we possibly could, and it was really interesting just to understand like how do you actually engineer it such that each particle is damping things as efficiently as possible.
Yeah, thank you. I don't know, Guan, did you lower your hand in between and it's raised again, or is this a leftover from earlier? Maybe it's the latter. Are there any last questions before I believe there's a chance to discuss more in breakout rooms? If not, then we'll just imagine the second round of enthusiastic applause and thank Dave once again. Thank you, Dave. And then I hope that I'll get assistance with the breakout rooms because I'm not in charge of those.
The breakout rooms have been opened, so you can join there by thrust, and you can join whichever one you'd like to.
Thank you, Donna.
You're welcome.
Thanks, Dave. That was great.
Good. Yeah.
Yeah, thank you, Dave, for the nice talk.
Yeah, it's great. It's great to see you.
Yeah, it's great to see you.
And do I have to do anything about this breakout room thing?
I think this hasn't really been working very well. The intention was for people to join by topic to discuss because the center is pretty big with a lot of people, but I think usually everybody is just gone. So
That's safe to say, yes.
Okay.
We're going to improve upon that.
Yeah.
Well, I'm happy to hang out if anyone wants to chat.
I can only see that one person has gone into the materials breakout room, so I don't think it's necessary.
I was in the devices room all by myself.
That's right. Camila is in the materials room all by herself.
I can just hang out in the main thing in case anyone wants to chat, but but no one should feel obligated.
Hi, Dave. Is that chiral lattice couple 2-qubit data fairly new? Is it published anywhere?
Well, it's not that new, actually,
Yeah.
but it's not published. We made the mistake of letting our student graduate and move on to a postdoc without finishing writing the paper, and it's been almost a year. So
I see.
But it's yeah. So we need to get it out.
Okay, cool. Yeah, because I was following that topic for quite a number of years by now, and yeah, looking forward to that.
Yeah, no, we're pretty excited, and I think and we sort of, there was a little bit of a lull between when that student graduated and we got new people on it. So, but I think we have a new postdoc from Andre from Andrew's group, and we sort of ramp it back up, and we have and a student who's sort of getting up to speed. So I think I'm hopeful we'll be able to start. I think the next step will just be putting 2 qubits in the system and then seeing how they can interact through it. But and then if we can do that, maybe then we can try crazier things like making some strongly interacting system or something.
Yeah, cool, awesome.
Okay, excuse me, is anyone coming to the breakout rooms, or they're just, or is this everybody staying in this main room? I went to the breakout room, there's no one there.
Camelia, I did too. I was in the devices room for a little while all by myself and decided that probably the main room was the better place to hang out in.
Okay, so I'll just hang out and listen then.
And I bet half of the people here just fell asleep, and
No, I think Donna mentioned early on that our breakout room attendance has been somewhat sketchy. So it's not you, Dave. I think it's a matter of people just scheduling for an hour and then just logging off mostly.
It's fine.
So this is a curiosity. My name is Camelia Okpodo. I'm a plant biochemist. And and I kind of joined the lecture a little late, so you probably had explained it, but I noticed on one of your illustrations you had excuse my ignorance of what you call this, but you had it set up. It looked almost like a several. It reminded me of a thylakoid membrane. And it was like you had like some tube set up, but it made it like an S shape. In it, when you were loading your 1 photons, and you were talking about. I don't know if you know what I'm talking, which illustration I'm talking about, but it almost like an S on the side.
I think I might. Well, here, let's just share it again, and we can look together. So, was it this thing? Or
yeah, that one.
Yeah.
The slide that's on the number 28. Yeah, the multi-mode cavity.
Mm-hmm.
Yeah. So was this intentional to look like a thylakoid membrane, or was this just something that you guys thought this made?
I think it's probably unintentional, so that fundamentally it's just a rectangular box, but because it's like a 1.5 foot long, and so we didn't want it to, and we have limited space, so we kind of wrapped it up. That's why it's sort of curled up like an S, just to take up less space. But fundamentally, you could think of it, it's actually like, you could think of it as like the electromagnetic version of like a flute or something like this. It's just like a long tube, and there are resonant modes in that tube, and like, and for each sort of like wavelength you can fit in the tube, you get a different note, just like you do for a flute.
But in nature, this happens. The way the thylakoids are stacked, they take up. There's sometimes the grana is linear, but most of the times, for when the plant is going through photosynthesis, the light harvesting complex is actually in that arrangement. So I think it's kind of interesting that nature has decided that is an optimal arrangement, and you have too. So
yeah,
I just thought it was very, very interesting. So
it's pretty. Yeah, I think trying to make wrap things up to for either to save space or to maximize surface area to volume is a pretty. That we definitely see that. We do that a lot in our stuff, and it's of course pretty ubiquitous in nature as well, both plants and animals.
Yeah, cool.
Yeah, like your I think your ear canal is also similar.
Yep. So you guys get to do the things that I dream about. I always wonder if I could just have 1 photon of light if I could just follow it around, and you're actually doing it. So
yeah,
that's cool.
That's the one thing we can do. But not in the complex and rich environment that you're in. We wish we could be at room temperature.
Yes.
I mean, some of my colleagues, I guess not really 1 photon. I guess some of my colleagues are they like blast the FMO complex with femtosecond lasers and try to see where the energy is going. So yeah. I'm surrounded on both sides by laser chemists.
Yeah.
I'm afraid they'll point their lasers at me sometimes and try and take over.
Well, if it ever comes to that, that they're actually probably just jealous because your work sounds really exciting. I'm a little biased here, but so.
Well, it is funny because my institute is physical chemists and physicists, and so the chemists are a little bit jealous of the physicists. But it's funny because the chemists actually know everything that the physicists know, and the physicists don't understand the chemistry like at all.
Yes. Yeah. They'll add some biology in it, where there's a derivation on a theme for whatever organism you're dealing with, and that just drives everybody crazy. So
yeah.
Well, thank you for your wonderful talk. A very inspiring thing to make me think about. I'm glad that I was able to join you guys, and I'm going to hop off and let someone else have part of the conversation. But I'm really impressed. I'm the dean of the College of Arts and Science at University of Wyoming. But my area of research, I study photosynthesis. Is one of the things I'm really much. I think it's my favorite subject. So anyway, very good. Thanks for including me, and I will see you on another time.
Yeah.
Thank you, everyone.
Yeah, thank you very much for taking the time. I'm sure you must be really busy.
Well, then, there's no one in the breakout rooms, so would you like me to conclude the call now?
There's
Sure.
some people who are still hanging out. We can give them one more moment of awkward silence
If
in
I
case they want
may,
to speak out.
can you hear me, Jens?
Yes.
Yes.
Yes. So, hi, David. This is Carlos Morales. I'm at City College. Nice to meet you. Wonderful talk. While you were discussing some of the cavities, by background, I'm actually a magnetic resonance person.
Yeah,
So
yeah.
I was wondering if there's experiments that actually involve some material spins in those cavities that you've had in mind. I can think of a couple already, particularly connected to, for example, generating nuclear hyperpolarization via the electrons spins that you may have with such huge Qs. I mean, there's a bunch of opportunities in there. I was wondering if you've thought about this or you're interested in thinking some more.
Yeah, so this was actually like a big part of my postdoc, and I've gotten to work with people who are now in the center. So with Steve Lyon in particular, and so yeah, we actually developed a technique to use these cavities, mostly the on-chip ones as opposed to the 3D ones, to be able to do EPR on really small samples. So if you wanted to do because with a normal EPR spectrometer, if you try to make the cavity smaller, eventually kind of the Q goes down, and it starts to suffer when you try to get to really small volumes, right? Because in principle, the singlet's noise only depends on the filling factor, but as you get smaller and smaller, eventually kind of the resistance just spoils the Q and it stops working. But if you have a superconductor, you don't have that problem. And so I mean, Steve is the one with the real EPR knowledge, but and has actually used it for useful things, not just demonstrations. But yeah, we use some on-chip resonators for doing that kind of thing. You can certainly do it with the these superconducting resonators as well. But that, I mean, because you end up putting them in a big field, they tend not to be. I mean, you probably it's easier. It tends to be easier to do on the chip. So I think the place where we found it to be really useful was where you had really small things. So like I think actually I haven't been doing it recently, but I think like Patrice Berthet in Saclay and Steve. I don't know if Steve has been doing it as much recently. So I think Steve got down to a few thousand spins, and I think Patrice may have gotten even further, at least for kind of very specifically chosen ones. But I think Steve kind of sort of more or less generically was able to get like something like 1,000 spin sensitivity, whereas like a typical commercial spectrometer might be 10 to the 10 or 10 to the something around there. So for certain types of samples, it could be really it can be good.
When you say sensitivity is what type of, I mean, is per square root of hertz or?
Yeah, like spins per square root hertz.
Okay.
Yeah.
Okay. Well, that's actually interesting to know. If you don't mind, I'll send you some material later once we complete it. But right now we're actually working on an idea that has to do with the use of electron spin noise to polarize nuclear spins. And so ultimately, you're imagining that you follow the thermal fluctuations of the electronic path, and by recording those and reacting on time. That's why I asked about the sensitivity. Then there's certain radio frequency pulses that you could put in place to polarize nuclear spins in the bath. And I was actually thinking of a physical implementation, a physical realization of those ideas. And so, well, I think that some of the resonators that you discussed today are really quite interesting as a possibility.
Yeah, yeah, no, and no, it is an interesting topic, and certainly at these temperatures, you can thermally polarize the electrons pretty easily. In principle, actually the challenge is that the electron lifetimes are too long. They can be hours or days if by themselves at these temperatures, and just in terms of spin lattice. So what you have to you actually the trick is actually like, how do you get the energy out of them sufficiently strongly, and cavities can help with that to some extent as well.
Yeah, well, as a matter of fact, I was actually thinking in terms of not so much about polarizing from polarization. You see, it's more polarizing about from the fluctuations. And so, the fact that the electron spins are not necessarily aligned is actually what we had in mind as a tool to use. I actually, unfortunately, I have a group meeting right now and I have to leave. But I'll send you, when the opportunity, when things are kind of better organized, I'll send you some material. And if you're interested, we can have a follow-up conversation.
Okay, sounds good.
Thank you very much for your talk. Very good.
Yeah, no problem.